So there are two ways of treating X-ray diffraction. The easiest and also empirical way is that we think about lattice planes. Lattice planes means it's a plane with array of atoms, for example. So physically there's no plane, but we can define plane, right? Physically there's no plane. There are only atoms, not plane. But we can define planes as we learned in the previous courses. And Bragg, B-R-A-G-G, in fact, it's a father and son. They both worked out together that if X-ray comes in, if X-ray comes in and diffracted from this plane, the next X-ray gets diffracted by next plane. Oh, I should actually draw this a little better. Try to centralize it here. And here. So that I can draw like this, and here's a perpendicular. Then we can see that the light diffracted by this plane and the light diffracted by this plane had the path length difference. Path length difference of this much. This is an extra path length that the lower ray had to travel, right? Okay? Because, here it's the same distance. Here it's the same distance. And then Bragg found that if this distance is integer multiple of the wavelength, then the top ray and the bottom ray constructively interfere. In other words, here's a top ray. I start from here. 1, 2, 3. It's almost like, you know what I mean. The bottom ray had 1, 2, 3, 4, 5 wavelengths. The top ray had 1, 2, 3, 4, but this point and this point are the same. So they are constructively interfering, or they add up the intensity. So that's why it's bright. But for this to happen, it has to have, this path length has to be integer multiple of wavelength that we are shining. Okay? So that's a Bragg's law. So basically, if we define this angle as a theta, this angle has a theta, then what you get is, and this distance of course is a d, as we define as a plane separation. Then this part becomes d sine theta. D sine theta. This is also d sine theta. So eventually what we get is 2d sine theta should be n lambda. Lambda is wavelength of the incident beam. Okay? And also outgoing rate too. Energy stays the same. Okay? So that's Bragg's law. However, this is empirical formula. And in reality, as I said, there is no lattice plane defined at least physically there's no existence of the lattice plane. So we have to look things in a different ways, and that's called Lao's formulation, Lao's law. Okay? So here we treat things differently. We choose, for example, 2 Bravais lattice point. It's an atom in a real space. Okay. Atom in a real space. And we have one light coming in and hitting this atom. We have other light coming in, hitting this atom. Same wavelength, lambda. Lambda. And lambda is 2 pi over k. Right? So it has also k. Okay? We can also define outgoing wave. The outgoing wave can go to here or here, either way. I mean, it can go 360 degrees, any directions. But what we want to find out is to which direction the light diffracted in which direction interfere constructively. Okay, this is what we want to find. This is what we want to find. So, for the convenience, we draw something like this. Here's an outgoing wave, K prime. Okay. And I have K and K prime because even though these are real space atoms, I can also overlay reciprocal space, right? So here what I want to do is to define K vector. K, vector K is coming in. Vector K is coming in, and vector K is going out. K prime. Vector K prime goes up. Okay, that's a vector. K and K prime are the same length because the wavelength is the same. Wavelength before and after scattering is the same. However, k and k prime are different vectors because it's a different direction. And because they're different directions, let me also define here n hot and n prime hot. You know what they are. You know what they are. I have to draw this parallel. This is a vector parallel to this direction of the length 1, length unity. And this is a vector in this direction of the length unity. Okay? Then I can start writing the following. Incident beam. Incident beam is k equals to 2 pi n hot lambda. Okay? K vector is n pi okay. The path difference now, the path difference is given by, here I draw a vector here. Let's just say this vector for the time being is d, vector d. Vector, do you want me to just put this? Just to make it vector? Okay, let's just say. And d, I say d because this corresponds to d here, right? Roughly. Not exactly, but roughly. Okay? So that's d. And if we do so, then the path difference is given by, I have to draw perpendicular line here and perpendicular line here. I have to define, for example, theta and theta prime, theta and theta prime, and the path difference in the same manner is this part. Path difference is this part. Path difference is this part. So this part is d prime length cosine theta, and this part here is d length cosine theta prime. And so I say d cosine theta plus d cosine theta prime. And you know, this is same as d vector dot n, because it's just an inner product of vector d to this projection, right? And this is same as this is same as minus d dot n prime hat. This d is different direction as this direction. So if you accept this and this, then this becomes d the inner product n minus n prime. Okay? And for these two rays to interfere constructively, the path length here has to be integer multiple of the wavelength. So that's, to have this condition, we say d dot n minus n prime has to be m lambda. M is just some integer. And we multiply both sides by 2 pi lambda. We multiply this both sides by 2 pi lambda. And if we do so, we get d prime 2 pi lambda n minus 2 pi lambda n prime equals to m, 2 pi. That's okay. M 2 pi lambda. And this is this. You see? This is this, and this is this. Right? 2 pi. This n. Sorry, this is 2 pi. Right? So if I insert this part here, it becomes d k minus k prime equals to 2 pi lambda. That's okay. 2 pi, yeah. Something is missing. Oh, that's right. This was 2 pi m lambda 2 pi lambda. So this is why I can erase this. So 2 pi m. Yeah. Okay. So then we ask ourselves, what is D after all? What is D after all? If you recall the previous lecture, D is practically same as R, right? It's a translational vector between Bravais lattice. Right? D is a translational vector between Bravais lattice. So this is, in fact, it is just a translational vector Bravais lattice, K minus K prime equals to 2 pi m. Then using this relation, remember this relation was derived for the condition that path difference is integer multiple. So this is derived in the condition for constructive interference. Constructive interference. So this, if we look at this relation, then I can say, okay, let's just use 2 pi m. Here, in the space, let me just write down exponential I 2 pi m. I just wrote this down, but 2 pi m equals to this one, right? So this becomes I r k minus k prime, and that is equals to 1, because this is 1, right? This is 1. This is 1. So you have seen this relation before. When did you see this relation? Definition of the reciprocal lattice vector. So this is exactly the definition of the reciprocal lattice vector. Right? So what it says is that, what this tells you that is that when k minus k prime is large K, when this vector is a reciprocal lattice vector, constructive interference occur. In other words, constructive interference occur only when k minus k prime is reciprocal lattice vector. What is k minus k prime? Here's k. Here's k prime. Here's k. And here's k prime. What is k minus k prime? K minus k prime is, in fact, this one, right? Yeah? So, the other way around. Yeah, the other way around, sorry. The other way around. K minus k prime is this one. Yeah. Okay? K minus k prime. Yeah, that's good. In fact, k minus k prime can go to this way and go to k, right? But I guess it's okay. It's the same thing. Yeah. Problem? Where are you? Okay. Huh?
Does the wavelength change in the material?
Wavelength doesn't change. We assume that wavelengths stay the same. That's why wavelength doesn't change. That's why this length is same as this length. Yeah, sometimes it changes, but for the time being, we just assume that wavelength doesn't change. Okay? So this is one particular condition, but just in reality, it is easy to show that. So what I said is that k minus k prime is k reciprocal lattice vector, and in this particular direction of k prime, usually incident beam direction is given. But outgoing wave, they go everywhere. But the question is which direction the light becomes very strong, scattered light becomes very strong. Right? Which direction? And then this is a way to find which way. And that is, if you know the incident beam, and also if you know the lattice, reciprocal lattice vector, then you can find out which direction the light becomes very strong. Okay? You can rewrite this in any way you like. For example, it is easy to show that k plus k prime k is also similar thing. Same thing. Same thing. Okay? So that's, that is also a condition to find constructive interference. It is also easy to show that after all, Laurent's formula, Laurent's law, and Bragg's law is practically equivalent, the same. And this is why this empirical formula is always used, because you can always think about reciprocal lattice, but sometimes it's too complicated. So sometimes you just look at the lattice plane. Okay? So it is easy to show it is the same thing. And it is actually written in every textbook. Okay? Okay? So what does this mean? What does this mean? So which direction lights intensity becomes strong is, this condition gives you which direction the diffracted light intensity becomes very strong. So here's what I'm going to do. I am drawing many reciprocal lattice points. Reciprocal lattice point. It's a time-consuming process, but this is what I'm doing, and so on. Okay, I just draw many reciprocal. There are many reciprocal lattice points here too. Everywhere. I mean, it's supposed to connect. So this is a reciprocal lattice point of the simple cubic lattice. In fact, this is just xy plane, but the same lattice continues in this direction too, right? Now, I perform experiments where I have crystal, and I send X-ray of the wavelength lambda into single crystal. And I want to know which direction the scatter wave's intensity becomes strong. That's X-ray diffraction. Okay? This is a simple cubic lattice, so I can draw simple cubic lattice reciprocal lattice points, even together with the real space. But this is what I have here. This is what I have here. This is what I have here. Okay? Now I can define the direction of the incident beam. And that's already given, because direction is here, this direction. So the direction has to be something like this. Right? And this is the incident beam K. Right? And then we want to know which direction the beam becomes strong. I said K plus K prime is reciprocal lattice vector, then that's okay. Let me write this down. So condition is K plus K prime is large K. Then light becomes strong. Also, there is a condition that K is same as K. In other words, the length of this vector stays the same. So automatically, I have to define something like this. I'll draw here. So, and the K and K prime has to be the same length. So now this is why I draw same length. Okay? So which direction does this condition fulfill? I'm going to draw a sphere around this center. This is called blob sphere. Blob sphere. Okay? And this particular point intersect with the sphere. What this means is that if I choose K prime in this direction, K prime in this direction, and this K plus K prime is a reciprocal lattice vector. Because here's a reciprocal lattice vector, this reciprocal lattice point at the beginning of K, and at the end of K prime, there's a reciprocal lattice point. So if I connect here to here, this condition is fulfilled. Okay? So this allows us to conclude that, yes, light becomes strong in this direction. So this is why you know already that in the light direction, parallel to this one, in the real space, we have screen. So the light coming on this direction become strong as the spots. Right? So this direction is parallel to this direction. So on the screen, we see bright spots. Okay? There's another point here. There's another point here. This has to be something like this because it's spherical. this also has to overlap. So light becomes strong in this direction. Light becomes strong in this direction too, right? There's another point, because it also comes in this way. There's a one point here which intersects with the sphere. So light in this direction is also enhanced. Light in this direction is so before I say something, before I say anything, I should have said this is a transmitted beam. This is a transmitted beam. So transmitted beam is always bright. Bright, right? And this is the one on the top of the transmitted beam. Okay, this point 1 is this one. Point 2 is the one below the transmitted beam. Below the transmitted beam. So here's point 1, point 2 is this below the transmitted beam. And if I have another point here to the right, I do have another point here which intersects with the sphere. So there's another point here, and there's another point here, and so on, right? That's the direction that you get strong X-ray diffraction. So if I just look at the screen, if I look at the screen, remember I had transmitted spots and the top spots, which comes from here, the bottom spot, which comes from here, the right spots, which comes from here, the one into the blackboard, which comes here from here, and each point is a reciprocal lattice vector. Yeah, it's a reciprocal lattice vector. So after all, you get this plus this is this, this plus this is this, and so on. So you get this kind of a square diffraction pattern from simple cubic lattice for 1, 0, 0 direction. This is 1, 0, 0 direction. Okay, this is just what we see on the screen. Is it clear? I hope it's clear. Is it clear to you? Okay? Also, there are other directions that you get diffraction. Of course, you know, this direction too. Because k plus k prime is reciprocal lattice vector. So if I had screen on this side, you also get similar pattern, right? I can even have diffraction in this direction if the particular points in this direction, particular reciprocal lattice points in this direction overlaps with the sphere. Then diffraction in this direction is enhanced. Okay? So this is sphere. And as long as you know the real space lattice constant or lattice structure, you can construct reciprocal lattice from which you can find which way X-ray diffraction intensity is enhanced. Okay? So this is one reason why we needed to learn reciprocal construction of the reciprocal lattice. Likewise, if let's say you are given sample with a strange, unknown structure. You perform X-ray and you get this kind of pattern. Immediately you know that, hey, this is like a simple cubic lattice or something else, but you get the idea. And this is how people determine structure of something using X-ray. So that's a Lao's method. Okay? So of course, if the crystal is rotated to 110, you get different diffraction pattern. Okay? And these are the homeworks. Little bit complicated, but you can work this out. Compared to what Nagasako group does, this is a piece of cake. It may appear complicated, but this is really the piece of cake compared to what Nagasako group does. Next, I would like to introduce different other method called powder method. Okay? The principle is the same, but now instead of one single crystal, we put powder at the sample position. Powder means collection of many single crystals. Collection of many single crystals. Okay, collection of many single crystals. So the answer is very similar. You get one diffraction pattern like this from one single crystal. And so I will draw this bigger screen. You get transmitted beam and transmitted beam and diffracted beam. And then here's single crystal. Here's single crystal. I shine X-ray, transmitted beam, some diffracted beam, and so on. What happens if I turn the crystal a little bit? Like this. This will rotate. This will rotate, right? So I get collection of new points. I'm going to draw already a circle here, just to let you know, but a collection of new points which comes, here's a collection of new points, right? Because I rotate it. And then similarly, I get points like this. Yeah. Let me see. This has to go to somewhere. Something like this. Okay? Something like this. Here's points. Okay? And so on. And then I have another rotated sample, and so on. And after all, collection of these rotated samples will give you these circles. And you get more circles. And so on, right? So that's what you get from the powder pattern. Now let me go back to some mystery here. First mystery is that how large is each reciprocal lattice point? If this is infinitely small, then it never overlaps, intersect with the sphere. If it doesn't intersect with the sphere, you never get constructive diffraction. This condition is not fulfilled. So the question is, how big or how small is each reciprocal lattice point? That is the question. It has to have some volume so that it can intersect with the sphere, right? What determines the size of the reciprocal lattice? Do you know the answer? No? Yes? What?
I guess.
You guess? Okay, please guess.
So, like we had in the homework, the volume in the direct lattice of an atom is connected to the volume.
Correct, that's it, right? That's, yeah. Yeah.
It's 2 pi over volume.
Right. That's right direction. And, more precise answer is that, remember, when we talk about Bravais lattice, real space lattice, we thought about infinitely large crystal. Sine wave, Fourier transform the sine wave becomes point only when sine wave is integrated from negative infinity to positive infinity, right? If you terminate the Fourier transform region, then this one point or peak with no width becomes broader and broader. So here, we are using X-ray to probe only the finite volume of the crystal. Therefore, because we're probing only the finite volume, we get finite volume, not the infinite volume, but finite volume, so that we get fattening of the reciprocal lattice point. Okay? For someone with a physics background, this formula might this is uncertainty principle, right? You've seen this momentum and position of the particle cannot be determined precisely. Remember this relation? Momentum and the position of the particle cannot determine precisely. And quantum mechanically, H bar K is momentum, right? So this becomes basically H equals to delta X H bar HK. Let's just say H delta K. H delta K. So delta KX, delta K is roughly 1. Roughly 1. That's the uncertainty principle coming from quantum mechanics. So position uncertainty and wavelength, wave number uncertainty are in the inverse relation. So here's delta. This is delta. Delta X. Delta X. For finite infinite crystal, for delta X is infinity, delta K becomes infinitely small, right? So that's why they become points. So, as long as we, in real life, when we perform X-ray diffraction, we probe this crystal with certain size. So, this point, size of this point is delta K. Delta K, because it's a reciprocal lattice space, K space, becomes big. And this way we get lots of overlaps. By the way, K 2 pi lambda is very large because we use X-ray. X-ray has very small lambda. So in fact, I draw this as an example, but real sphere becomes practically flat. It's a huge radius, right? Huge radius. This is like a radius. So it's practically flat. So this is why we see many diffraction spots like that. Okay? Diffraction spots like that. It's practically, it's a flat. The next important point is how shall we define the origin of the reciprocal lattice? Origin of the reciprocal lattice in this case. It is convenient to choose this particular point as the origin of the reciprocal lattice when we talk about diffraction. Okay? So this is origin on the screen. Now we have to define x, y, and z direction. Let's say this is x. No, let's just say which way is good. If this is z direction, we have to say this is y and this is x. It has to go like that. Okay? So this is x and this is y. Sorry, it's different from what you usually see, but let's just say this is the way I define. Okay? Then, this particular point is 0, 0, 0. It's origin. And this point is 1, 0, 0, right? The bottom point is 1 bar, 0, 0. 1 bar is minus 1. Yeah? This is 0, 1, 0. So this is 0, 1 bar, 0. Okay? So after that it's easy. This vector plus this vector is, this point is 1, 1, 0. And this part is 1 bar, 0, and so on. And this is 1 bar, 1, 0. Then this is 1 bar, 0. Right? I'm talking about these points. And in this case, the light direction, this direction is 0, 0, 1. Right? 0, 0, 1. So, after all, you find that Miller indices, this is HKL. HKL. It's Miller indices. So it's a 1 bar, 1, 0, and so on. And I say this spot is a diffraction from 1 bar, 1, 0 plane. This spot is diffraction from 1 bar, 0, 0 plane. You know, plane after all. If we want to connect what we do to the Bragg condition, then of course, you know, we always talk about plane, diffraction from plane. So this is a diffraction from 1 bar, 0, 0 plane. To be precise, it doesn't make sense if you talk about Bragg diffraction condition. Do you see what I mean? 1, 0, 0 plane is parallel to the incident wave. Right? These are the plane. We have these plane. And I have incident beam. And I say, even though the incident beam is parallel to this plane, I get diffraction spots. So I said Bragg condition and Laue condition is the same, but yes, it's true, but because of this point having volume, this overlaps with this sphere. So this is off from Bragg condition, but still we observe diffraction using Laue's condition. So in that sense, Bragg condition is not always true, but you know, Laue's condition gives you more practical solutions. Do you understand do you understand the discrepancy? 1, 0, 0 plane, I said I have light coming in like this, and I have many 1, 0, 0 plane parallel with the light. In this case, Bragg condition says there's no diffraction. But there is. わかるってこと？わかんない？全部平行でしょ、線が、面が。そこにいきなり平行にライトが入ってきたって、ブラックコンディションは満たせないじゃん。実はこっちに回るっていうことを。いや、それでこっちが球面になってるんだけど、その球面に本当はこの点は球面で球面とは交わらないんだけど、この点がボリュームがあるから交わってそっちの方に光ってくる。So to be precisely speaking, this direction is not the diffraction is not allowed, but because there is a volume, we get diffraction spots. Okay, so the last part of the lecture, I will cover so-called structure factor, and then I will explain what those homeworks are. At least, you know, I need to translate what they are to you. Okay? So remember, some crystals, you don't have to draw this. Some crystals are not Bravais lattice. So for example, this kind of a honeycomb structure is not a Bravais lattice. So you have to treat some pairs as a what we call basis we call these are bases. And then these bases form Bravais lattice. Okay? And we have to treat everything in terms of Bravais lattice so that if I shine X-ray here, Laue condition, remember, we have K prime and K and so on. But so you know, we treat them first as if they are single atom. But then we have to think further whether these two atoms, presence of these two atoms, whether maintain the constructive interference or not. Maybe presence of these two atoms distract the strong intensity. Okay? So that's what we have to do. So let's think about diffraction by bases having two atoms. So basically, condition is that this and this should be K prime, right? That's the Laue condition for constructive diffraction. However, what is the effect of actually these two on the actual constructive interference? This is what we are going to do. Okay? In each base, let's say we have D1, D2, Dn. N means that we took some origin somewhere. Maybe we took origin here. Maybe we took origin here. And this is D1 and this is D2. Oh, okay? Well, we took origin somewhere. It's arbitrary. You can take it anywhere. But the point is that because there are two atoms, we have D1 vector and D2 vector. Okay? So we need to find path difference between D1, D2, and so on, right? So the path difference is given by K. Path difference is given by K dot di minus dj. The path difference is that this projection to D1 and D2, for example, gives the path difference between this and this path. Okay? And if this is a path difference, then phase changes. Phase changes by exponential I k dot d I minus dj. So this is for one particular base. In practice, we have many bases, and all these bases adds up to the intensity of the X-ray. So in a real X-ray, we define so-called S sub k, which is basis j equals to 1 to n, E exponential I k dot dj. It's the same thing, but it's just a and this is called structure factor. Structure factor. Structure factor. Structure factor. Okay? So this gives you basically the intensity of the X-ray diffracted. Intensity of the X-ray diffracted. Okay? So once we define the structure factor, I can tell you how to use it. So I will use a specific example. Specific example. Let's treat body centered cubic BCC. Treat BCC as a simple qubit. I always think about quantum bit. Cubic lattice with a base D1 equals 0, D2 equals to A over 2 X Y Z. Okay? X, Y, Z. So this is as if we are saying, this is D1, this is D1, and this is D2. This is D2. This is D2, right? Because D2 is A over 2, X hat, Y hat, Z hat, right? So we now treat them as a pair, base. We treat them as a base. Then once we treat them as a base, we will have simple cubic lattice. Right? Simple cubic lattice. Simple cubic lattice. So now this we have A1 equals AX, simple cubic lattice. A2 equals AY, A3 equals to AZ. Right? This is just three primitive vectors for the real space. Simple cubic lattice. And of course, reciprocal lattice. Of course, the reciprocal lattice is a cube of a side 2 pi over A. Now, let's calculate the structure factor. So structure factor is given by this. Structure factor is given by this. So here, S, K is sigma J equals 1 to 2 exponential I K D J, that is exponential 0 plus exponential I K dot D2, and that's 1 plus exponential I K dot D2, that's 2 over A X plus Y plus Z, right? Now, so now we have to represent K somehow. So I put K, reciprocal lattice vector, as a 2 pi over A N1 X hat N2 Y hat plus N3 Z. Make sense? Yeah? And of course, because this is a reciprocal lattice vector, this is just, all I'm saying is that B1 is 2 pi over A X hat. That's all I'm saying, B2 and B3. So now I'm going to insert this. I'm going to insert this here. But if I calculate, we do the same thing, right? This and this is 1. Y hat is 1. Inner product of Z and Z is 1. But Y, X is 0, and so on. So if I insert this, what I end up is SK structure factor, that is 1 plus exponential I pi N1 plus N2 plus N3. After all, only this ZZ N3 part survive. N1, N2, and so on. Okay? And this is 1 plus cosine pi N1, this is just N1. I don't know how to pronounce this as Euler's relation. Plus I sine pi N1 plus N2 plus N3. And this is 0. Pi sine times integer is 0. So this, after all, is 1 plus minus 1 N1 plus N2 plus N3. It's either 1 or minus 1 because these are integers. It's either 1 or minus 1. So this becomes 2 when N1 plus N2, N3 is even. And 0 when N1 plus N2 plus N3 is odd. Right? So now we get the structure factor. For a simple cubic lattice, so let's think about what this means. Okay? Here's a challenging You're going to see what I'm going to do. Okay. So I hope you get the idea of what I'm trying to do. So I'm just drawing a cubic lattice, right? Right now. Here's the origin. Okay? Here's the origin. This is origin, so I say this is Z, this is X, this is Y. And this is a reciprocal lattice point. Okay, this is a reciprocal lattice point. So here is a reciprocal lattice point where n1 is 0, n2 is 0, n3 is 0. Okay? So we call it 0, 0, 0. This is 0, 0, 0. And because this is x direction, this is 1, 0, 0. Right? This is 0, 1, 0. This is 0, 2, 0. This is 2, 0, 0. This is 1, 0, 0. Sorry, 0, 0, 1. This is 0, 0, 1. This is 1, 0, 1. And this is 2, 0, 1. No, yeah, this is 2, 0, 1. And this is 2, 0, 2. 0, 0, 2. 0, 2, 1. 0, 2, 2. So this is, now this is 1, 2, 2, 2, 2, 2, 2, 2, 2, and this 2, 1, 2. Okay? I can even go farther, 0, 2, 0. 0, no, 0, 1, 0, 1, 1, 0, 1, 2. Okay? Everything's not consistent. This is 0, 0, 2. 1, 0, 2. And this is 1, 1, 2. Okay. So now I'm going to see which one is even and which one is odd. Okay? I'm going to circle with red those that are even. This is even. What else is even? This is odd. This is even. This is odd. This is even. 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 What is it? Middle. Right? Even. 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 And I'm going to cross out with yellow, because I haven't used yellow, those that are odd. And so on. So now we have You see, we started off with a blue simple cubic lattice because originally we thought about simple cubic lattice. But we thought about structure factor. And we found that those that are even are red circles, and those that are odd are yellow crosses. And I said, this has a strong amplitude, right? That's what structure factor does. And this amplitude is 0. So practically, the intensity is 0. So all I'm saying is that those yellow point disappears. Yellow reciprocal point disappears. What is the structure of the red? It's a face-centered cubic. Remember? Reciprocal lattice of the body-centered cubic is a face-centered cubic. So that's what we get. So everything makes sense. Everything makes sense. I say this again. Reciprocal lattice of body-centered cubic is a face-centered cubic. Even if we consider body-centered cubic as a cubic lattice with 2 bases, and go through all the structure factor calculation and so on, physics is always the same. At the end, we get face-centered cubic as a reciprocal lattice of the body-centered cubic. Okay? So this is something that, for example, Professor Nakasako's group and all the other structural analysis group does. They have to think about, okay, there are many atoms within this basis. And maybe they construct or maybe they destructively interfere. And they analyze everything, whether everything is consistent with what they observe as the diffraction spots, with what they think is a real space lattice. Right?